So we're going to start a new unit today, and so for the next couple of weeks we'll be studying authentication. And so essentially, we set up systems where users can post public keys on networks. Then any other user could send a message to whoever set up the public key, and the contents of that message would be secure in the sense that nobody but whoever set up the public key would actually be able to read the contents of the message. However, there's still a big potential security issue here, um, which is identity authentication. So if Alice is sending a message to somebody claiming to be Bob, how does Alice know that it's actually Bob who set up the public key? Or if Bob's receiving messages from someone claiming to be Alice, how does Bob actually know that Alice sent those messages? And so the way we're gonna kind of deal with this issue is with authentication protocols. And so this is basically ways where people can publicly associate information with themselves, and then use that, or allow other users to use that information to verify that they're the ones actually responsible for publishing public keys or sending messages. All right, and so the idea is so digital signatures essentially are going to be some sequence of bits that we're going to append to a message that's going to somehow serve as authentication that the source of the message was actually the person who claimed to be sending the message. But of course, since the digital signature is just a sequence of bits, it can be easily reproduced. So the way around that is that to have security against forgeries, so signatures are going to have to depend upon the message as well as the sender when we're doing a digital signature, right? So unlike paper signature, so if I sign a piece of paper, nobody's going to be able to use that exact signature without mutilating the paper and trying to paste it onto another piece of paper. And so this is something that should be fairly easily detectable. When we're sending digital messages, so the way around this is that the signature is actually going to have to depend upon not only the signer but also the message. Right? So every message that I sign with my digital signature is actually going to get a different signature, a different sequence of bits. So nobody can take the sequence of bits I use to send one message and try to apply that to another message. Okay? All right, so a digital signature scheme then consists of A, a method by which a user is going to produce a signature Y on a message M, and a method by which recipients can verify that Y is a valid signature on message M for user Alice. Okay. All right, we're going to look at public key signature schemes. So where Alice sets up and publishes some parameters then that anybody can use to verify Alice's signature. All right, so the first signature scheme we're going to look at is RSA signatures. Okay, so we're going to have Alice set up this scheme. Okay. So Alice is going to essentially generate an instance of RSA. So she's going to set up two large primes, P and Q, public modulus N, which is going to be P times Q, chooses a B, which is going to be invertible non-phi of N. Okay, so as usual, I'm going to calculate A, which is going to be B inverse non-phi of N. This all looks like RSA so far. So then Alice is going to publish B comma N and keep A, P, and Q private. Okay. All right, so we can think of A then as Alice's private. If we're thinking of RSA, it will be a decryption exponent. And then B would be a public, so we can think of it as an encryption exponent. Okay, so now Alice wants to send message M, and so Alice's signature on M is going to be M to the A reduced mod N. And so then Alice would send the pair M comma Y. Okay. And so notice then Y is essentially the decryption of M in this instance of RSA. Right, because it's the message raised to Alice's decryption exponent. Okay, so this looks kind of strange, right? So M is a plain text message. So if we were trying to do cryptography here, we wouldn't actually be decrypting M at all, right? We'd probably be encrypting M. But when we're doing a signature, we're going to send what's essentially the decryption of M. Okay. All right. But the reason for this then is that this can easily be verified, right? So Bob wants to verify. So Bob's gonna download the public exponent in the scheme, the public modulus. Bob is going to compute y to the b mod n. So this is essentially encrypting back that signature. And then if z is equal to m, then the signature is valid, right? So why is that? Well, what's y to the b? Right? Y was m to the a. Okay, but a and b are inverse exponents of each other in this instance of RSA, so that should just give me m. Okay. So if we have a valid signature, then everything should verify. Okay. All right, so we have any signature scheme. We want it to be secure against forgeries. Okay. All right, and so there's really two types of forgeries that can occur. And so the first type is a selective forgery. And so selective forgery means that the forger has some given message X in mind and can produce a valid signature on the given message X. Okay, so the forger can find a signature, call it Y, such that X comma Y will actually verify. Okay. Second kind of forgery is what's known as an existential forgery. And so this means that the forger can produce a valid message signature pair for some message, but has no control over what the message is. Okay, so in general, we want security against selective forgeries. Okay, so we certainly don't want anyone to be able to choose a message and produce a valid signature for that message. Okay, so if that were the case, then right, we would have absolutely no security in this scheme whatsoever. Right, so somebody could sign all sorts of messages. Right, so it could force Alice to sign IOUs, claiming that she owes millions of dollars to the forger. Right, and so we would have absolutely no security under this scheme. With the existential forgeries, as we'll see, so this turns out to be way too much to ask for in these public key signature schemes. So there'll pretty much always be existential forgeries. But the thing about this is it'll be very low probability that the corresponding messages will be anything meaningful at all. So it's really nothing to worry about as far as security goes. Okay. All right, so let's look at RSA signatures and see if either type of forgery can be produced. Okay. And so we'll assume that Freddie the forger has access to the public parameters of the scheme and maybe even a valid signed message. Okay, so what would have to happen in order for Freddie to be able to produce a selective signed message or selective forgery on a signed message? Okay. All right, so Freddie then wants the signed message M. So what does Freddie need to do? He needs to find Y such that, well, the only way this is going to check out, right, since verification and signing are inverse processes of each other, the only way this is going to work out is if Y is actually produced according to the correct signature scheme, which is to say that Y is actually congruent to M to the A mod N. Okay. But A is essentially the secret exponent in an instance of RSA. Okay, so this amounts to breaking this instance of RSA. All right, so in other words, the RSA signature scheme is exactly as secure against selective forgeries as the RSA crypto system is, right, against the breaking of the system. Okay, so this is as secure as the RSA crypto system. All right, so what about existential forgeries? Okay. All right, well, so now if I'm Freddy, I'm just going to work in reverse here, right? So I'm going to start with a signature. Okay. And I'll call it Z just to distinguish from what we were doing in the previous part. Okay, and then, all right, so if I have a signature in mind, right, then I know how to produce the message that the signature will verify, right? I just apply the verification process to that signature. Okay, so then I'm going to let call X just be Z to the B mod N. Okay, so then clearly the pair X comma Z verifies, right? Because I just obtained X by producing whatever had to be equal to the original message under the verification condition. Okay. All right. However, what is this? Well, this is X is essentially then the encryption. So X is an RSA encryption here. Okay. And if I take any Z whatsoever, and I encrypt it under RSA, I'm going to get a string that just looks like a bunch of random nonsense. Okay, so I have no control over X here. So it's very unlikely that I can't target a message, right, as we saw in the first part, without breaking RSA. And it's very likely that I could get a message that's going to correspond to anything meaningful without breaking RSA. Okay. Furthermore, if we want to, we can require in our communication scheme that there be some redundancy built into messages. Okay, so messages would have to have some check bits, some parity bits, and so then it's even less likely that I could get something that's a meaningful message, such that all the check bits verify. Okay, so essentially, then all these existential forgeries are always going to be possible under these public key signature schemes. They're really never anything to worry about, right? Because we can build in robustness against these type of forgeries into our system very easily. All right, so now here's a little variation on the signature problem that we can also use RSA signatures to solve. So suppose we want to do blind signatures. Okay, so again, suppose Alice still has a signature scheme set up, but basically she's using it to sort of notarize documents for other people. Okay, so Alice is verifying that that other people have the contents of these documents. And suppose Bob wants Alice to sign a document for Bob, but he wants Alice to do this without seeing any of the contents of the documents. Okay, so maybe Bob has some important discovery, but wants to make a record that he has priority over the discovery, but is a little paranoid about information getting out. So wants Alice to sign it without actually being able to read the contents of the documents. Okay. All right, so there's a way we can do this, and so we'll use a scheme that's known as RSA blind signatures. Okay. And so again, suppose that the message to be signed is M. Okay, so here's the protocol. So again, Alice is going to set up an instance of RSA signatures, so just like before. So public parameters MB, private parameters P, Q, and A. All right, and again, since we're just using ordinary RSA signatures here, so we can now say that the desired signature is going to be M to the A, okay, in Z mod N. right? Because that's, so if the message to be signed is M, then the signature is M to the A. All right, so what Bob is going to do is essentially put a mask on the message. So Bob's going to choose a random integer k in z mod n star. And so k is going to kind of serve as a mask. But the thing is, we need k to be on the signed message rather than on the pre-signature message. Because Bob needs to be able to remove the mask. And the way Bob is going to remove the mask is going to be by multiplying by k inverse. But if it's not just k on the signed message, Bob's not going to be able to remove the mask. Okay, so what Bob's going to do then is, in the message that Bob sends to Alice, multiply by k to the b instead of just multiplying by k. Right? Because Alice is going to sign this by raising it to the a. Right? By k to the b to the a, because b and a are inverse exponents of each other, mod phi of n is actually going to reduce back to k. All right, so Bob's going to compute t, which is k to the b times n. Okay, going to send that t to Alice. Okay, so Alice is going to sign t by computing s, which is going to be t to the a mod n. Okay? And then Bob is going to get the correct signature on the message m by removing the mask. Okay, so by doing s times k inverse. Okay, so this recovers the signed message. All right. Okay, so let's verify that this is actually correct here. Okay, so so this is the t. Okay, so what's s? So s is t to the a, but here's t. It's k to the b to the m to the a. And just by rules of exponents, that's k to the ab, m to the a. Okay. All right, but again, a and b are inverse exponents of each other in this instance of RSA. Okay, so it's just k times m to the a. And so then when Bob does s times k inverse, well, that's ma times k inverse. It's just m to the a. Okay, so that's the correct signature on the message. Okay, so essentially then we design this so that we pick the right thing to multiply the original message by, so that when Alice raised it to her power, we were left with just this easily removable mask. Okay. All right, so that's RSA signatures. So next time we'll look at a few other signature schemes that are going to be based on the discrete log problem.